So, the other big thing I wanted to emphasize this section was function notation. So let's dive right into that. And again, this is all in the textbook. There are videos from the publisher. I love this publisher. I would not use them if I didn't like them. So again, this is just supplementary, but the function notation is, important enough that I'll feel better about myself as a teacher if I provide a little introduction as well. So let's say you have a function. And you've got an input and an output. And a lot of times, the function is going to take the input, it's going to do something mathematical to it, and the result is going to be the output. For example, let's define an area function. Let's take an input. Let's square it and multiply by pi. So I sort of gave the game away with the name, but what this function is doing is it's taking as its input the radius of a circle, and it's giving as an output the area of the circle. Well, we've talked about we've talked about the idea that some functions can be represented as equations, right? A equals pi times the radius squared. So this is a very compact way of getting this idea across, but it's not function notation. It's close to function notation or close-ish, but it's not quite there. So here's how function notation works. When we have a function, we give that function a name, and we need to give the input a name. We don't need to give the output a name. And function notation is the name of the function and then the input in parentheses equals, and then over here is whatever happens to the input. So returning or keeping with this example, this function is giving us an area. So let's name it capital A for area. And the input is the radius. So let's Name the input to lowercase r. So the name of the function, the input in parentheses equals. What's happening to the input? Well, we're squaring it and we're multiplying it by pi. And just by convention, we write in that order. And this, when we read aloud, is read of a of r equals pi r squared. And this is function notation. And if we have an input, what is the area when r equals 2 inches? Well, we write that. We go here and we want to know what happens when r equals 2. So we just replace the r with the 2. And we say a of 2 equals pi times 2 squared or 4 pi. And we could get a decimal approximation if we wanted it. So that's the basic idea of function notation. But why? And I ask that question because it's probably already occurred to you that this thing, which I said isn't function notation, and this thing that is function notation look really, really similar. So the question, it's a perfectly valid question to ask, why? What am I getting out of this? And the answer is just that function notation is a lot easier and a lot more compact in a lot of situations. Like here, I ask a question. What is the area when the radius is 2 inches? With function notation, we can write this statement very compactly. When the input is 2, the output is 4 pi inches squared. Now, if we weren't using function notation, we could still address this question. We could still answer this question. But not as compactly. So function notation saves time, it saves space. And at the moment, it might not seem like we're getting all that much. But especially, for example, here's a formula, the average rate of change formula. For a function f of x on an interval from A to B. And this example is not one I'm choosing at random. We're going to come back to the average rate of change formula. It's actually quite important in calculus. So the average rate of change formula is f of b minus f of a divided by b minus a. Nice, simple, and compact. Suppose you weren't using function notation, though. I mean, suppose you just have as your input a variable x, as your output a variable y. So you do have a function, but you don't have function notation. Then this turns into y when x equals b minus y when x equals a divided by b minus a. Clearly worse, right? So function notation is really important just for being able to write math compactly and efficiently. One thing about function notation, again, it's not my intention to review everything in the textbook, but this is important enough that I'll state it explicitly. We can have complicated inputs when we're working with function notation. So f of x equals x squared minus 2x plus 1. So x is the input if we want to know the output when x equals 2. F of 2 equals 2 squared minus 2 times 2 plus 1. If we want to know the output when the input is 3, 3 squared minus 2 times 3 plus 1. And you see this pattern where the input is here. The input is showing up on the left and on the right. So here we're replacing the x with 2 on the left. We're also replacing the x with 2 on the right. We are replacing the x with 3 on the left. So we're replacing the x with 3 on the right. What if the input is something complicated? Instead of a nice number like 2 or 3, what if I want this to be my input? Well, it really doesn't change anything. So our input is x squared plus 2x minus 3. So we go up here. Everywhere that x appeared, we replace it with this new input. So we've got this squared minus 2 times this. So having a more complicated input didn't fundamentally change how we work with functions. And I mean, just looking ahead a little, we're going to be really, really interested in situations where our input is x plus h. Never mind y for the moment, but keeping with this function, we go over here, and everywhere that input x shows up, we replace it with this new input. So there's functions. I mean, many of you have probably worked with functions already in high school, for example, but if not, you're going to have plenty of time to practice because we'll be spending almost this entire semester working with functions. There's, I think, maybe one section of the textbook where we have something else. But overwhelmingly, calculus is the study of functions. It's how functions change over time, or more specifically. Well, it's a lot of things, but among other things, it's the study of how functions change over time. Let me see.